hier muss es sein. Kommt da?
GMs over the ground field and split over E is over E. So in other words, the way you think about it, you have these lattices, D to the R, D to the D, and you have a finite group acting on these lattices. And so the toric and homomorphism between lattices give you dually homomorphisms of the right groups. So locally and globally, we have extensions of local fields, we have local Galois groups, and then our lattice M characters, so it carries the action of gamma, but it also carries the action of the local gamma V, and so we have all these different groups acting on the lattice, and we along the invariant sub-lattices, and so on. So relevant for us is that we have a map from T points modulo. Now, so that notation is like in the repeating. So what I mean is the following. You can fix a model of T over integers. And then at almost all places, the maximum compact subgroup will be indeed the integral points of the torus. But at finitely many places, I mean, there's no such thing. So then I just take the maximum compact. So let's just take at almost all places it really is integral points of some model of T over the integers. And the basic fact is that we get an embedding of this as a sublattice into the gamma V invariants of the lattice M. And for almost all V, for those unramified in E, again, the splitting field is not unique. It's just amplifies the gamma V extension. So if you take the bigger one, that's what it is. For almost all V, we get an idomorphism. So this model that is indeed the gamma V invariant of the big lattice. So the adels, we have a torus over the adels, and we have the kernel of the characters, rational characters, T1 or T. So if you've never seen these kind of things, just think about GM. Over the rational, so we have GM of A, the adels, right? So, and inside we have the G1. Well, that's all those which have absolute value 1. So the absolute value, you have makes sense. And inside those with absolute value 1, you have the rationals. And that's just the product formula. You take some rational number from 0, you take a product formula, and product of all multiple absolute values is 1. So you have this sitting in here in general as well. And then there is the product of the compacts, and basic structure theorem is that, alright, so the adel corresponds to the kernel of the character, so that's not surprising that it's sort of isomorphic to the dual gamma V invariant center R, and in the classical case GM, it's just R, right? So you have the absolute value, and it can make not real value. Now the T1 modulo Tm is compact, and the intersection of the rationals with the unit with the compact is finite, so this is the unit. In the classical case GM, so you have GM of Q modulo of the compact, and then it's like plus minus 1. And in the general case, it's like the units. Alright, so we will be using the characters of this group to become apparent now. And so we need to have kind of a picture of what these characters look like. So you have a map from this quotient, the idyllic points of t, modulo tf and kt, to the Archimedean component, and in the Archimedean component summer will be mv, so m gamma v, then there r. So it's a real vector space, okay? And in that space, we have characters sort of dual to t1, t modulo t1. So that's that space. So that's mr, m gamma r. And the rest is a lattice. So again, in the standard case of GM, it's a classical case. So this is, when you think about it, you have an embedding, so you have a logarithmic mapping, right? So you have absolute value, and then what's left is that the units embed as a lattice into whatever's left, yeah? And then you see like R1 plus R2 minus 1, so that's what's happening. So this is sort of R1 plus R2, and then the minus 1, that's this space, the one-dimensional unit space, and then what's left inside the lattice. And so, anyway, so this follows from this is compact, and dual to this group. Toric varieties. So that was sort of the basics and background of algebraic tori. Now, our setup from yesterday was we have some algebraic group, in this case a torus. We have a representation in PPLN plus 1 in X of projective space, Dn. If you pick a point, we look at the closure. And so what are these varieties? Now, in case the group is a torus, representations are parameterized by discrete data. I mean, they know the form, representations of tori. And so the varieties which we get are also kind of rigid and discrete. And, well, then you want to get an understanding of how do we build such varieties, how do we think of them intrinsically without needing reference to representations. And so this is a theory of toric varieties. It's a very combinatorial theory. And let's start with the simplest example, P1. Alright, so P1, we have the torus GF, algebraic torus sitting in P1. The complement has 2 points, 0 and infinity. And so there are other distinguished open subsets. There is an A1, the complement is 0, and the other A1 is a complement to infinity. And so this is like A1, and I want to think about it like this, and here I want to think about it like this. And so you have duality. So maybe I don't want to write like the X here, I just like f of z greater than 0. But keeping in mind that actually I'm only talking about monomials and the corresponding exponents of the monomials. So you have z, which is sort of here, is dual to 0, and you have z greater than 0 dual to this and this dual to that. So you have 3 semigroups, and okay, so maybe I just make a picture. So the way we think about P1, combinatorially, it's so we have a space of co-characters n, in this case just d, and we have 3 distinguished colons in it, so 1, the other, and 0, and in the dual picture in M, we get these distinguished semigroups, and then we glue them somehow. For example, this GM, it sits both in here and in here. And those two, A1 and A2, intersect. It's an intersection GM. And so this is a combinatorial description of these gluing data, group data, and it's a general case split, meaning now tori isomorphic to products of GM looks like this. So we take M, like d to the d. So we have a dual group, and we have a fan, which is a collection of cones, just like here. So the cones, this is the cone, this is the cone, and this 0 is also a cone. And now, so 0 is in every cone. condition, then you would get non-complete toric. The affines in ACM is also toric variety. And then you have sort of every phase of a cone is in this collection, and the intersection of two cones is also, first of all, the phase of both of these, and secondly, belongs to the Feynman sigma. So you want to exclude some cases where the cones sort of intersect and everything your points intersect this. So it's really a subdivision of your space n to the r by cones, and cones in various dimensions. And if you like, just pick maybe n vectors, e1 up to en, and those vectors will be spanning cones, some of them will be spanning cones, and so that's the picture. In fact, the most difficult part here is to distinguish between m and n. It takes many years of hard work to figure out this, and it's essential in the work, it seems, keeping in your head what is m and what is n. In any event, when is such a thing regular, just a notation, if you can extend generators of every cone in this band to a basis of the whole lattice. So we have a lattice in place, and then you have a lattice that is real. And so the cones here, we think of them being generated by lattice vectors. So that's essential. And we want that every cone generated by part of the basis. So what's the output? We start with these sort of combinatorial things, and then we produce these basic affine varieties. So what's written here? M, remember, was just a lattice. And lattice intersected with a dual cone, well, it's just sort of a cone, a semi-cone. And we think of that as being sort of the exponents, it's x to the m. Alright, so then we can multiply, so the x's go x1 equal to 3, which is called exponent, so that's what we have, some basic affines. And then we glue those affines, and the conditions which we have here on these intersections and faces, and they just translate into what we see for P1. So one affine, another affine, they intersect, and intersection with another, affine, and so on. Okay, so that's the picture, that's the definition of what toric variety. There is sort of an interpretation that the generators of the bands, so these are both the one-dimensional, so one-dimensional cones, generated one-dimensional cones, correspond to boundary dividers, reducible components of the boundary. And then with geometric properties, the smoothness is ensured by this similarity condition. So we've seen P1, and the other toric variety we should put on the board is P2. So here the picture is like this. So we need the two-dimensional lattice. So here again, P2, and well, so your 1, 0, 0, 1, your vector, so maybe E1, E2, and minus 1, minus 1. Okay? So, and again, so you have 3, so inside you have GM squared, and then you have, in the complement you have 3 lines, and those 3 lines boundary divided correspond to these 3 vectors here. So this point would correspond to the GM sitting inside, so this is the GM, and then there are the affines. So these two-dimensional cones correspond to points, the intersections of these lines, and this is how you translate sort of the combinatorial data into sort of geometric data. Okay? Well, and then there are these A2s which you from here. So that's geometry, and in the split case, so this is how it is. And in the non-split case, so you know, you can list varieties by actions of the Taylor group. So we have this group gamma, finite group, acting on all these lattices. And we call effect theorem is that, and so there's a totality here, if you take a complete fan, which is, well, regular and gamma invariant, and in addition, if we know that the corresponding Toric variety, the one we group, is projective, so that's a property that you can read off from the fan as well. That's some convexity properties of the fan. I don't want to go into this. Then, in fact, there is this fan. There is a complete algebraic variety of the ground field with the property that the field extension to E produces this Toric variety, which we already understand, the split Toric variety. Okay? And in fact, well, you have E varieties here and there, with gamma action, so compatible, and the non-split torus T will act on this variety. So this will be an equivalent multiplication of the non-split torus T. So the only subtlety is, well, if you don't insist on projectives, then this descent may not produce an algebraic variety of varieties. This will be an algebraic space. So the first example, or basic example of algebraic space. And you can develop a series of rational points on these spaces and count the points of all type and you have a neutral phi. So for our purposes, and the proof is sort of not sensitive to space or variety, but I don't want to stress this.
Can I say?
Yes.
So the Galois group in that last slide.
Yeah.
So the Galois group is coming from the fact that you started with GM or a Toric variety for some field, then you looked at the characters on that thing, the dual, that, and then you use those two lattices to build the thing in the split case.
So I start this lattice, which over the field extension, I mean the lattice, I start with a gamma model. So I have this representation. So I have this Toric picture. I have an algebraic group, which over the ground is whatever it is. For a field extension of the model to GM, I have the actual finite group on the characters, the co-characters.
Okay.
So I want to get an equivalent multiplication of its non-split forms. So this is a picture. You pass through the field extension. You use the fan structure, the combinatorial structure, to...
But what is the fan structure on? Is that on the space of characters?
It's a fan structure in the space of co-characters n in the split case. So it carries the Galois action as well. So I insist that the Galois group doesn't move cones into something else. Alright? The images of the cones and the Galois group are still cones in this fan. Once I have this, in reality what happens is that you just see the picture to be sort of very symmetrical. So for example, you could imagine here an action which just exchanges these two, this kind of symmetry, D2 symmetry, and then that would be an invariant, gamma invariant fan.
Okay.
And then you would be able to descend somehow. And in general, so produce very symmetrical looking fans. And then the theorem is that, alright, if you work with the splitting field, you have this compactification and these combinatorial things are compatible, then you can descend to the ground field. So, and well, the descent questions I think were discussed in the previous lectures, yes? But this is a very concrete realization of that. I was thinking about that.
That's right.
Yes.
So you get the action of the torus over
Yeah. So you get the action of the torus over F into the ground field on X sigma F. So that's the point. Yeah, it's a finite group. So it's a finite group. So everything splits over a finite Galois extension. And so you have a finite group, I think, on that's what we had in the first slide, and Toric correspond to. That's exactly what's happening. That's why it's system progress. Exactly. Sorry? You want to keep the torus action. So you want to get a Toric variety. So if you just take the quotient I mean, how do you know that all these things are compatible? Well, so, I mean, you're of course right. If you have a variety, projected variety, that much to take invariance, that's what you do. So you want to keep your two data, your algebraic forms, P, all is split into, embedded into your projected variety. You want to keep the group action, the equivariant property. Well, it's from the 60s, I mean, right? It is a basic fact. It's not a Richter field, but this is what you have to check. Okay? Now, Picard proof. So some geometric invariance of arrays. Well, we know that getting the Picard proof amounts to take any divisor, use the group action the divisor to the boundary, then it's going to be a sum of some boundary components, the sum coefficients. The coefficients are integers. So, and the relations come from characters. Now, the way it's encoded in the Toric picture is that you speak about piecewise linear z-valued functions. I mean, it sounds very complicated. What is it? So you want functions that are linear on every cone of your fan. But how do you get a function that is linear on every cone of your fan? Well, if you have a function that's linear on every one-dimensional generator, well, that will be it. Because, right? So in other words, it's a phi system prescribes the values of your function on one-dimensional generators. But you have n of those, and they correspond to the boundary component. So if you prescribe n integers, so for each e1, e2, en, so here, for example, so p of pj, so you prescribe some number, some integer, then you get yourself a divisor. So that's what it is. It's just a sum of boundary. But for reasons, you want to think of that as being piecewise linear function. That's the reason. And the relations are the characters, and the Picard group is just a function, boundary components by the relations. Now that's in the split case, and in the non-split case, well, you just have a gamma action on this whole thing, and when you take the gamma invariance, then you pick up an each one. And the zero comes from the fact that the boundary components are permuted by the Galois action. In other words, this is a permutation model of Galois, and H1 of the permutation model is 0. And H1 of gamma m is the final. Alright. And we had it in front of us yesterday, but not for time. So what's the effective cone? The effective cone is the image. So I should probably put this picture on the board because we'll be using it many times. So you have this fundamental exact sequence in the split case. And so how do we get the cone of effective divisors? We take the simplicial cone spanned by the boundary components with negative coefficients, and we project with respect to the, well, m under r, and that will produce some polyhedral cone in the Picard group under r. So that's the picture. And as we discussed yesterday, you can get any cone you like, basically, by playing with different dimensions as an action to generate. That's it. The n-canonical class is the image of the sum of the boundary components. So, so let's call this phi, so phi, and the n-canonical class is just phi of the sum of the boundary component. And it will be convenient for us to introduce standard coordinates here. Well, we have these distinguished vectors, d1, d2, dn, so we may as well write every divisor as sum of si, di. And so it's like the image of the vector 1, 1, 1, 1. Projection. Okay. So now we have the geometry. We move on to heights. So here is the way to define height of a pylon. For example, the height of a point Well, x0, x1 are non-zero. So you would look at, say, x0 over x1, we are equal to if you have this, and x1 over x0 otherwise. Okay? And then you have a product formula. So you look at this product over all HV, and you will see that what's written here is nothing but maximum of x0b, x1b, and the product over all b on the rational. So that's exactly the height we work with in projective space. So the height maximum coordinates are b and the product over all b. And in general, the heights are defined as follows. So we have this embedding into NB, which is an isomorphism of lattices for almost all B. And on NB is this. We have this piecewise linear function. That is a function that is linear on every cone. Okay? And we just take QB, which is P of the rational, to the power value of the piecewise linear function of the image of x, the VI component of, xv, under this map. So this is like the logarithmic map. So in the Hermitian case, it's just a logarithm of the absolute value of what's written here. And the non-Hermitian analysis, that's like the logarithm. And so you take the value of the piecewise linear function here and then 2b to the this. That's the height. And it's exactly this in case of P1, and then we take the product of all B. And so here we have a dependency on the choice of this piecewise linear function. So what happens? So for every element here, you get so comparing with an adelic form. And for the Archimedean ones, QB is E. So E, not E. So get a pairing between the adels and the, who says we need to pick the value piecewise linear function? We may as well tensor PL sigma this to complex numbers. So piecewise linear function is determined by its values in one-dimensional generators. Well, the Sj are now complex numbers. So we have a pairing between this and this to complex numbers. But if we restrict to the rationals, then in fact, by the product formula, if we take a global character and take the value of the character on the rational point of the torus, and then take a product over all B, we get 1. That's the product formula. So the pairing descends to the pairing between rational points and the complexified Pythagorean. Because it's just trivial on that. When you restrict it to the rationals, not on the adels. So here you get a pairing in the complexified Pythagorean and rational points of the torus. And if you further restrict to line bundles, so an element of class L and the Pythagorean without C, just honestly, then you get height as before. So projective embedding, which is very ample, and then maximum coordinates. So what is happening here is the following. So toric varieties, you get actions of tori on all those spaces. So to define a height, we need a basis for space of global sections of some line bundle. Well, it turns out that you can always pick a basis consisting of monomials. And then you have these monomials, and then our definition of maximum coordinates. So maximum coordinates is to be maximum of the d-adic values of these monomials. But for these monomials, all that's relevant is sort of the exponents of these monomials. And then we are into this picture of this piecewise linear picture. We live in somehow in this space, and we're pairing this with that. Alright? So that's the height. Now that we have the height in place, we can immediately observe that just by the very definition, it's TOB invariant. So that's how we put it. We look at TFB modulo TOB and map it into ND, and that's what we have. And then we have this data function, sum over all rational points of our height. Now I begin to write T of S, where S is sort of a vector as far as to Sn, and T of S, remember that Ej is Sj. So I want to Doric is my preferred coordinates in this space DL of sigma. Okay, so we have a zeta function, sum over all rational points. Now, this height is defined on the adel's. So we have some function defined on the adel's, and now we are averaging over the rationals. So you have something which is on TAF modulo TF. And the first thing that comes to mind, well, okay, we are in the L2 space, TAF modulo TF. And let's do Fourier analysis. Let's do Poisson formula.
So the vector S is Radical component.
So this piecewise linear function is determined by its values. Maybe I should write it here. So in PL sigma will be determined by its values on one-dimensional generators. Now which as J are complex numbers, and just to remind myself that when I have this as J in place, I write it like PS and S is the vector now, okay? Well, that's good. Maybe it's sort of ambiguous notation, but I want to remind myself that I have fixed on generators, and now I'm just working with complex function or something. In any event, I do the standard thing, I write down the Poisson formula. So Poisson formula goes like this. So a priori, T8 modulo TF dual of the Fourier transforms of my function. Okay? And then, so I integrate on the characters. But now, I use the fact that the height function was invariant under the TOVs, under the action of the complex subgroups. And therefore, it's invariant under KT. And as you know, in Fourier analysis, when we integrate a function that's invariant under some character with a character, then it disappears. We saw it in the first lecture when we read these delta functions, integrate a non-trivial character, then we get 0. So that's what we get. In other words, already I have some kind of simplification. On the dual side, I integrate over this space of characters, so Fourier transforms of heights, and again, so there is some, I took height to the minus s, right, in my zeta function, and so the minus somehow propagates equal. Alright, now for the non-trivial ones, it's 0, and to apply the Poisson formula, well, I need to know something about convergence, so the left side and right side. Now the left side, the definition of my zeta function, well, that converges just from the projectivity. So if I assume that my Toric variety x is projective, then I get the convergence for s big enough for free. Okay? Absolute convergence. So the convergence of the other side, of the spectral side, so to speak, well, that has to be checked. As in fact, later on we'll see why it converges. I mean, you have to compute these Fourier transforms explicitly. And then, of course, well, there are R measures, as usual, the definition of the Fourier transform. I mean, you know this thing. I mean, you take E2, 2 pi I, or you take E2 pi I, and you dx, or dx and square root of pi, or whatever. So you have to normalize your R measures to something. And the next step is the computation of the Fourier transforms, of the local Fourier transforms. So let's do the simplest case. So P1. So we have this P1, and in the picture we have here the characters of P1 or Z. And the piecewise linear functions, I mean, there are 2 points in the complement to GM, 0 and infinity. So 2 dividers. So there are S1 and S2 coordinates of my piecewise linear function. And the Picard group is a projection of Z plus Z modulo Z. Right? And the Z is sort of embedded, the way it's written here, it's plus 1 from the other, and minus 1 in this direction. So, what I need to do, I have an embedding into, well, this, at final places, I have an embedding into this lattice. So at each prime, I have sort of a one-dimensional lattice here. And I have a piecewise linear function, which on this component of the lattice is something like p to the like minus s1 onto this component is b to the minus, well, s2, but then, yeah, and that's what you have, except that, well, maybe n, here it's like n, and let us vector n here, minus n, and now I need to integrate, so I just have to sum over the lattice a function which on the right side looks like p to the minus s1 times n, and on the other side p to the minus s2, well, absolute value of n, and we have two geometric series, and one geometric series is here, so I already put in the character, and the other geometric series is here, so that's a character, and the character gets embedded exactly the way this n gets embedded over here. Okay? And alright, so this is one geometric series, another geometric series, but now I have to take into account that I counted 0 twice. So it appeared here, it appeared here, so I have to remove it, so I get the minus 1 here. Okay? Because p to the 0 after all. And at the infinite place, it's very similar, so it's the same kind of analysis. And we know how to integrate such things, so you get this and that, and then it's the 1, because now the intersection of these constants are very different. So that's your P1. So what does it give? The data function of P1, depending on two complex variables, S1 and S2, so it lives on this space under C, is an integral, so these are the characters, over the m, of data S1 plus IM. So this is what happens when you put these things together, except that there is data, I mean, something is missing, data over S1 plus it's missing here. So let me write it down here. So data of P1, S1, S2 becomes an integral over R. So zeta S1 plus IM, zeta S2 minus IM, and then divided by zeta S1 plus S2. All I did is I put together these expressions, and so these are the zeta factors and denominators here, and there are some translations happening here, and the contribution from infinity is S1 plus IM plus 1 over S2 minus IM dn. So this is a very complicated way of counting points on P1. I mean, P1 after all. X0, X1, we know what the end is. Whatever. But, of course, the point is that here it's easy, but for general varieties it's not so easy. And if you want to bootstrap what you see, the general varieties. So we need to analyze this integral and understand its analytic properties. So already you are seeing that, okay, so to integrate over m, suppose S1 and S2 both have field part bigger than 1. So then these are just bounded. This is not dependent on m. So this whole thing is just bounded. So we need to integrate this. On each term here is not integrable at m. But there is a cancellation happening when we put these terms together. And so the Archimedean component will in fact be integrable over m. So this will be integrable and this is bounded. So the whole thing is holomorphic for real part S1, S2 bigger than 1. And then we need to understand the poles. Wherever we get the poles, there we have the poles of the zeta function, right? Then we need to get a continuation to the left. And, well, then it's not true anymore that zeta function that is bounded by constants. We integrate over m, vertical strips. We need to understand estimates on zeta functions and vertical strips. So it uses the function equation for the Riemann zeta function. It uses the triangle principle. And we know that in the neighborhood of 0, so that is for S1 and S2 being, so the neighborhood of 1, being close to 1, within 1 minus epsilon, the zeta functions are bounded in vertical strips by m to the epsilon. And this is still 1 over m squared. And so the answer will still be integrable, but then there is some residue. There are some residue computations involved to get the pole and the constant of this pole. So this is the simplest case of the analysis, and so I encourage you to do this exercise. We'll try to harmonically continue this integral and try to see what's happening. Now, already, if you look at the pole, what's the residue at s equals 1 here and here? Well, it's 1 over 1 plus 1 or 1 over zeta 2, and that should strike well. This is what happens when you count points from all the time that you want. We have like b to whatever power, and then from the co-primality position, we have 1 over zeta 2. So this is the 1 over zeta 2 going up. General case. In the split case, well, we have the same situation, except that now we're summing over all these other cones. And so we sum over cones, and for each cone, of course, you get a product of geometric series. So for each cone, you get a product over the generators of this cone, and that's where we use that we have a smooth variety of whatever you have, so corresponding Sj, and then Ej m. So this is the embedding of m into this space. So if you want to know the coordinates, so these are the coordinates. Now, and this plus minus 1, that's, well, when you start summing over cones, then the cones are counted twice in smaller dimensions, and then you remove them, but then you remove too much, and then plus minus. So that's a combinatorial picture. So you sum over cones in every dimension of this plus minus 1 of a product of geometric series. And at the Archimedean places, well, when the cones intersect, you get no contribution. So you're just summing these kind of expressions. Sj plus I, Ej m. That's it. And then we put it all together. First look at the one-split case. So we have the sequence that's basic to us. It gives us dually a sequence of points. Sorry, it's not like the adels. Now that's also the adels. For permutation module, that will lead to a very special chloride. It's just a section of scalars from the corresponding fields defined with the factor for summit of this permutation module, Fj over F Gm, the section of scalars. And then the characters of this, well, you can map them to the corresponding characters here. And so you get k characters, I1 by k, and it is known, so that's the theory of algebraic order of the delta, that this map has a finite order. And it's essential in the unification of the constants. Alright, we put everything together. It's a similar analysis to what we had before in the split case, but now, for each place V, we have the group gamma V acting, and we have to look at the gamma V invariant subspaces. So it's like we begin to cut our space by its gamma V invariant subspaces, and do this kind of summation, plus minus over the cones, in the subspace. Alright? And, well, in higher dimensions, so at some places the whole thing is completely split, at other places it was not split, and then we sort of want to keep track of that. And well, the answer is that the whole other products which you obtain will be regularized by L functions from the corresponding fields. Okay, this coordinate Sj, what is it Sj now? Well, now they correspond to boundary components over the ground field. So this chi1 up to chi k. So this is just the splitting of this permutation module into, say, sigma 1 up to sigma k unions of dividers of the closure, which are Galois invariant. Yeah? So these are the pieces of the boundary which are defined for the ground field. And over the extension, they will split further. But over the ground field, that's what they are. And so those are the outcomes which we get. And the bottom line for us is that when you look at this formula here, you sort of already see that when you put all these summations together, in the denominator, you see sort of local factors of some L functions, L function 1 minus QB, and, well, how many of those? Well, as many as you have one-dimensional generators, ej, and so that's, well, or rather the gamma invariance, ej running from 1 to k, and then you get something in the numerator, and well, there are some miracles happening, combinatorial miracles, and that cancellations lead to the fact that whatever is left, in sort of the numerator, the denominator, is in fact an absolutely convergent product product in the domain we're interested in, that is the neighborhood of 1. Okay? So remember that we want to understand analytic behavior of this data function in the interior of the form of effective dividers shifted by the n-canonical class, which is 1, 1, 1, 1. Whereas in this case, we want to understand the behavior of our data function in the neighborhood of 1, 1, 1, 1. And we'll be seeking continuation to 1 minus delta, and what you get is in fact for 1/2 plus something, this is bounded and therefore irrelevant. And then you have some contribution from the infinite factors, which, well, we will need to integrate and sum. So the space of characters, as I explained, was, well, a lattice and times this m gamma r. So you'll have an integral like this, you'll see it in a second, and you'll have an infinite sum like that. Alright, so here is an integral over the continuous characters, and here's the sum for all these other characters, t1 modulo t3kn. So that's a lattice. Alright, and so we need to be able to sum the Fourier transform and then to integrate the outcome. So we need estimates on somehow, well, the m from before, and then there is also an estimate on the components of the character under the embedding tag, go down at the beginning into the median components. And that lattice, so a character has also a certain size, namely wherever it sits on that lattice. And there's a natural norm, the natural norm of the sum, and b, and infinity. Alright, so the infinite Fourier transforms give us bounds necessary to integrate, and the final places give us the poles. Where we have the poles, where the characters are trivial, and then we just say the data function in Sj, which is a pole s equals 1. So we have to analyze these poles. And here comes our friend from yesterday, the function, the poles, and the corresponding Laplace transforms. So that's the function of the poles. So lattice, dual lattice, this is the function. But now, we want to think of, so okay, so here we have the pole, and here we have another pole, and we have a subjection, so from one pole to another, induced by subjection of lattices. So suppose we have any homomorphism of lattices, and it's an induced sort of subjection of the poles. Suppose we have some co-kernel, which is finite. Here there is no co-kernel, but remember when we have the gamma invariance, we have a finite co-kernel. And then we have some kernel, then we normalize the volume somehow. Then Poisson formula. So space, subspace, and so you look at this integral. In fact, the alpha function of the image is equal to the integral over the relations of the alpha function of the source. And those factors are just normalization, and so here it just comes from the duality. Alright? So in particular, in the case you're interested in, so the alpha function of the simplicial cone was just 1 over s minus 2 over s the ring. So that's the alpha function of the simplicial cone of this cone here. And then we have relations which are m's. And then, well, if you integrate over the relations of the alpha function, then you get the alpha function of the image cone. Now look again at what we have in this picture. So in this picture, the poles were data function Sj. Now data function, each has a pole at s equals 1. So s equals 1 is exactly the translate of that canonical class in this picture. And then we integrate over So if we had 1 over product of the SJs here, then we would see exactly an integral expressing the alpha function of the image cone, which is the cone of vector diagonals, or modulo the shift plus minus 1. But what you're seeing is something much more complicated than that. So now we need to have some kind of residue calculus that would reproduce the meromorphic properties, or proof meromorphic properties, analytic properties of the height of the function based on what you can say for in the standard case in the key function of cones. So that's that. And that's the technical part. That's where residues this and the other. So what do we know? We know that if you take this product as 1 minus 1 and then as n of n k depending on the notes to minus 1 of this sum of all the other characters and the big characters, it is in fact holomorphic in 1 minus delta. That is, the polar part really comes from, well, we have to take the function of both as 1. And if you take the pole out, then the thing is holomorphic. But moreover, you also have gross estimates which come from Frank and Lindemann. So we look at this expression and we take out the poles S1 minus 1 and S2 minus 1 that we write in here. And then what's left? Well, it satisfies certain gross estimates. And then we also need to understand the constant at these poles, the leading constant. So what happens when S equal to 1 is, and we get some number, and in this case what happens when S goes to 1, we see, here the residue is 1, here is 1, and here we have 1 over beta 2, and here we have like 1 over 2, 1 over 2, the Canadian component corresponding. So suppose we have these properties, then there is a big technical result, which says that in fact, the data function will be holomorphic in, well, this shifted cone with this and the S's project into the shifted cone shifted by the economical class. We will get a meromorphic continuation to a tube domain over a neighborhood of this point. Now, this is sort of the last thing which I mentioned yesterday. The complex analysis part. So here we have this cone, effective, and well, there's some shift and economical class. And so a tube domain, in general, a tube domain is just a domain of Z so that, well, delta, real part, Z in delta. So the real part is fixed and the imaginary part is everything. Okay? And then there's a theorem in complex analysis in some complex variables which says that, okay, suppose you have some domain and you have a function which is holomorphic in the tube domain or that domain in Rn. Well, then, in fact, it's holomorphic in the tube domain over the convex closure. So you close up, you take the convex closure of this domain, then you get automatically holomorphic continuation to that. So what are we doing? We are working in a tiny little neighborhood of the point S1, S2, as j equals to 1. Alright? And we're going to get meromorphic continuation with poles described by this alpha function of the complicated arrangement of hyperplanes in a small neighborhood of this point, the minus k point. And then to the tubular neighborhood. And then by convexity, we get it even far away from this point. So if we understand the polar structure here in the small neighborhood, then by this convexity principle, we also understand it far away. So this is where it really shows that you need to work in the whole complexified Picard. If you just wanted to work with one line bundle, variable line bundle, then you wouldn't be able to use the theorem, and then it would be difficult to do it. So in any event, so we get meromorphic continuation with the poles as we expect, so from this alpha function, and then we need to look at the constant at the highest order pole right here, so the leading coefficient. Now to identify this, the theorem is that well, you only look at what happens here, and then the corresponding leading constant here will be just the product of what you had here with, well, the leading constant of the alpha function. And that, remember, was just one factor in the asymptotic formula. So remember that the number of points is alpha, beta, and tau, and the alpha is this. The alpha is from here. So right now the analysis just pulls out for us. So one of the constants in the asymptotic formula. So then we have to somehow identify the beta and the tau. Now to identify the beta and the tau, we have to do the Poisson formula one more time. And we have to use the theory of Toric. We have to recall the finite kernel that we had when we were mapping the character into its components, phi1 up to phi k. And once we do that, then we can identify the remaining factors, beta and tau, so that lots several pages of recalling instructions for Toric. Use all computation of some gamma numbers in Toric to all. And then, well, we've only done the proof in the neighborhood of this point, and we obtained the morphic continuation far away, but we haven't identified the constant in the other points. And remember, I wrote down the other constants are sums, infinite sums, or sum distributions. Well, that requires a version of the theorem which I sketched above. And again, get it done. That's the Toric picture. I know it's sort of not much of a graph, but through the slides and paper for the web. Tomorrow we'll be doing the additive case, which is perhaps easier from the point of view of analysis. There are not going to be any residue calculations like this, but it's quite interesting from the point of view of geometry. So that's how it works. So you see that there is a lot of technology going into looking the counting points of all the type of different varieties. Well, thank you very much.